Hello guys, you are welcome. In this video, I will guide you through understanding binomial theorem with clear explanations and step-by-step examples. Before we begin, if you are yet to subscribe to this channel, please go ahead and subscribe now. And don't forget to turn on the notification bell so you'll be alerted on future uploads. Now let's dive into the business of this video. What is a binomial? Binomial is made up of two Latin root words, bi and nomen. Bi means two, and nomen means name or term. A binomial is the sum of two terms raised to a power. To begin with, we will consider the binomial of the form a plus b raised to the power n, where a and b could be a mix of constants or variables, and n could be any natural number from 0 up to infinity. The general expression for each term in the expansion of a plus b raised to the power n is the product of n combination r, a raised to the power n minus r, b raised to the power r, where r is an integer starting from 0 to n for each term. Before we proceed, let me briefly refresh your memory on operations involving combination from the last video and then expand on them to establish some facts. We've already established that the formula for n combination r is equal to n factorial over n minus r factorial times r factorial. Now let's use this formula to find some combinations. Example 1n combination 0 is equal to n factorial over n minus 0 factorial 0 factorial. This is equal to n factorial over n minus 0 is n, so it's still n factorial. Remember, we established that 0 factorial is equal to 1, so this is times 1. So this is equal to n factorial will cancel factorial, n factorial. So all of this is equal to 1. Now, n combination 1 is equal to n factorial over n minus 1 factorial times 1 factorial. Now, this is equal to n times n minus 1 factorial over n minus 1 factorial times 1 factorial. N minus 1 factorial will cancel n minus 1 factorial. So we are left with n over 1 factorial is equal to 1. So it's equals to 1. So we have here that n combination 1 is equals to n. Now let's try with an actual number to prove this, to show you how this flows. Let's try with 4 combination 1. This is equal to 4 factorial over 4 minus 1 factorial times 1 factorial. This is equal to 4 factorial over 3 factorial times 1 factorial. This is equal to 4 times 3 times 2 times 1 over 3 times 2 times 1 times 1. Now, looking at this, you agree with me that 3 times 2 times 1. We can also 3 times 2 times 1. And this can also be expressed as 4 times 3 factorial over 3 factorial times 1. So 3 cancels 3, and then we are left with 1. So I did this to show you how, now, you know that going down, each successive term is just the first term minus 1. That is 4 minus 1 equals to 3, like that. And that's the whole concept here. I just did this for you to fully understand this. So the next thing we will look at is n combination n. This is equal to n factorial over n minus n factorial n factorial. This is equal to n factorial. N minus n is 0 factorial n factorial. Remember that 0 factorial is equal to 1, so we are left with 1 n factorial over n factorial, which is equal to 1. So these are the three things I want you to take note of, that n combination 0 is always equal to 1, irrespective of what your n is, whether 1 million, whether 1,000, whether 6, whatever n is, n combination 0 will always be equal to 1. Also, note that n combination n is also equal to 1. That is 10 combination 10 give you 1. 1 million combination 1 million will give you 1. And finally, n combination 1 is always equal to n. 100 combination 1 will give you 100. 5 combination 1 will give you 5. 4 combination 1, just as you saw here, will give you 4. Having established those facts about combination, let's see how that applies binomial expansion. Now, we've already established that we are working with the binomial expressions of this form, and then we established that the general expression for each term in the expansion of a plus b raised to the power n is the product of n combination r, a raised to the power of n minus r, and b raised to the power r. Now, let's start with n equal to 0. That means a plus b raised to the power 0. Now, you agree with me that anything raised to the power 0 is equal to 1. But let's prove that with this formula here. That is the expression for each term. So, our n is equal to 0. Combination r is equal to 0. And then we have a raised to the power n minus r. Our n is 0. Our r is 0. 0 minus 0 is 0. And b raised to the power r. Our r is also equal to 0. So from the facts we stated about combination, we know that 0 combination 0 is equal to 1. And a raised to the power of 0 is equal to 1. B raised to the power of 0 is also equal to 1. So therefore, this is 1. That's a plus b raised to the power of 0 is equal to 1. Now let's try it with a plus b raised to the power of 1. A plus b raised to the power of 1. In this case, we are now using this general expression. We have that the first term is 1. In place of n, we put 1. Combination r is 0. And then a raised to the power n minus 1. That is 1 minus 0. 1 minus 0 is 1. And then b raised to the power r. R is 0. So this is 0. We already established that n combination 0, anything combination 0 is equal to 1. Then a raised to the power 1 is a, and b raised to the power 0 is 1. So our first term is 1 times a times 1, a. Then we'll continue until our r is equal to n. Our n is 1, so we can go again. So we have 1, c, our r is 1 now. A, n minus r, that is 1 minus 1, 0. B is 1. B raised to the power r, our r is 1. So this b raised to the power 1. So this is equal to 1 combination 1. Remember, we established that n combination n is equal to 1. So this is 1 again. And then a raised to the power 0 is 1. And then b raised to the power 1 is b. So we have here 1 times 1 times 1 is equal to b. So therefore, a plus b raised to the power 1 is equal to the sum of each term. Now let's move on to n equals to 2. A plus b raised to the power 2. Now you agree with me that this is the same thing as a plus b raised to the power 2 is equal to a plus b times a plus b. Now the whole concept of binomial expansion is just a shortcut to achieve this multiplication without going through the long process of multiplying. Let's prove that here. So our n is 2. Our r in this case is 0. N combination r. A 2 minus 0 is 2. Our r is 0. This is 0. So we have b raised to the power 0. So, sorry, this is 0. Our r is 0. So 2 combination 0. Anything combination 0 is always equal to 1. A squared and b raised to the power 0 is 1. So we have here that the first term is equal to a squared. That's 1 times a squared times 1. Then we move on because our r is not yet equal to our n. Our n is 2. So we can go further. So this is 2 combination 1. A n minus r in this case, that is 2 minus 1 is 1. And then b raised to the power r, our r in this case is 1. So 2 combination 1, remember we established that n combination 1 is equal to n. So this case we have 2. And then a raised to the power 1 is a, b raised to the power 1 is b. So we have here 2ab. And then we continue because our r is still not yet equal to n, but this will make it equal now. 2 combination 2, a 2 minus 2 is 0, b raised to power r, which is now 2. So we have, remember, n combination n is equal to 1, so 2 combination 2 is 1. A raised to power 0 is 1, b raised to power 2 is b squared. So we have 1 times 1 times b squared, we have b squared. So a plus b squared raised to power 2 is equal to the sum of each term, which is a squared plus 2ab plus b squared. So you see, it's the same answer as if we would have gotten as if we distributed this into this to multiply. It's the same thing. So binomial theorem is just the shortcut of expanding. So let's move on to 3. In this case, our n is equal to 3. That is a plus b raised to power 3. So using this formula for each term, we have 3 combination 0, 1, 0 for r. So we have a n minus r, that is 3 minus 0, we have 3. Then b raised to power r, which is 0 here. So we have anything 3 combination 0 is 1. Then we have a cubed, b raised to power 0 is 1. And then here we have a cubed. And up next we have 3 combination r here is 1. A 3 minus 1, n minus r is 2. Then our b is 1. So this is equal to, remember, n combination 1 is equal to n. So we have 3 a squared b. This is equal to 3a squared b. Now, remember, we continue until our r is equal to 3, is equal to n, which is 3 in this case. 3 combination 2, we have 3 a raised to power n minus r, 3 minus 2, this is 1. And b raised to power r, this is 2. So 3 combination 2 is equal to 3. So we have 3a b squared. So all of this is equal to 3a b squared. We continue until our r is equal to n. Our n is equal to 3, so we continue. We have 3c combination 3. Then a raised to power n minus r, that is 3 minus 3. So we have 0. And then b raised to power r here is 3. So this is equal to, by n combination, n is equal to 1. So we have 1. A raised to power 0 is 1. And then we have b cubed. So this is equal to 1 times b cubed is equal to b raised to power 3. So we have that a plus b raised to power 3, which is the same thing as a plus b times a plus b times a plus b. So instead of going through the drudgery of this multiplication process, you just use this, and then the sum of each term, we have a cubed plus 3a squared b plus 3ab squared plus b cubed. And finally, let's do for the last one, 4a plus b raised to power 4. I'm just doing this to prove a point, to just show you how easy it is. So here we have 4 combination 0, a raised to power n minus r. Our n is 4, our r is 0, so this is 4. B raised to power r is 0. So 4 combination 0 is 1, a raised to power 4, b raised to power 0 is 1. So we have here a raised to the power 4. Next one is 4 combination 1, a raised to power n minus r, that is 4 minus 1, 3, b raised to power r, which is 1. So we have here, this will be equal to 1, a raised to power 3, b raised to power 1. This is equal to a, no, sorry, 4 combination 1 is equal to 4. Remember, n combination 1 is equal to n. So we have 4a cubed b raised to power 1. And then up next we have 4 combination 2. A raised to the power 4 minus 2, that is n minus r, is 2. then b raised to the power r, which is 2. So we have here 4 combination 2 is equal to 6a squared b squared. This will give us 6a squared b squared. We continue until our r is equal to n, which is 4. So we have 4c3 a n minus r, 4 minus 3 is equal to 1, and b raised to the power r is b raised to the power 3. So this is equal to 4 combination 3 will give us 4 times a times b raised to the power 3. So this is equal to 4a b raised to the power 3. And then finally 4 combination 4, our r is now equal to n. So a raised to the power 4 minus 4 is 0. And then b raised to the power 4. So we have this is equal to n combination n is equal to 1. So this is 1, this is 1, and this is b raised to the power 4. So we have here b raised to the power 4. So a plus b raised to the power 4 is equal to the sum of all the terms, which is a raised to the power 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b raised to the power 4. Now this is the same thing as saying a plus b times a plus b times a plus b times a plus b. So instead of going through the drudgery of multiplying all of that, your binomial expansion helps you do that with ease. Now, let's take note of some things here. First of all, number one, note that a binomial raised to power n will have n plus 1 terms. Now, this is a binomial raised to the power of 0. It only has 1 term, which is 1. This is a binomial raised to the power of 1. It has 2 terms. This is a binomial raised to the power of 2. It has 3 terms. 1, 2, 3. This is a binomial raised to the power of 3. It has 4 terms. 1, 2, 3, 4. And so on and so forth. It goes on like that. It's like a law. And number 2, note, in a binomial expansion, the term corresponding to r is always in the r plus 1th position. That is, this term now corresponds to r equals to 0. So r plus 1, 0 plus 1 is equals to 1. So it's the first term. Let's pick something random. This. Okay? This corresponds to r equals to 2. So r plus 1 is 3. So that makes this the third term. 1, 2, 3. Do you understand that? And then finally, note that the sum of exponents in each term is always equal to n. Now this is a plus b raised to the power a plus b raised to the power 3. We see that in each term the exponent is equal to 3, equal to n. This a raised to the power 3. Then we have here a squared and b. The power of b here is 1. The power of a here is 2. 2 plus 1 is 3. Same thing here. The power of a here is 1. The power of b here is 2. 2 plus 1 plus 2 is 3. Here the power of b is 3. And all the sum of the exponents in each term is always equal to n. That's what that means. Let's now move to binomial theorem. There are different ways the binomial theorem is expressed in textbooks, but it essentially boils down to this. The expansion of the binomial expression a plus b is the sum of all the terms as r runs from 0 to n, with n held constant. And this is the mathematical expression for binomial theorem. Now let's solve some examples. In this example, we have to expand the following. 2 plus x raised to the power 5, x minus 1 over 3 raised to the power 3, 1 plus x raised to the power n. Now let's get into it. Number 1, 2 plus x raised to the power 5. Now remember what our binomial theorem is. That's what we'll be applying in here. And our binomial, so in expanding this, using the formula for each term, we have 5 combination 0, 2, in this case, 2 is our a. 2 raised to the power 5 minus 0, and x raised to the power 0. Plus, remember we'll continue until our r is 5. 5 combination 1 raised to the power 2, 5 minus 1, x raised to the power 1. plus 5 combination 2 raised to power 5 minus 2 x raised to power 2 plus 5 combination 3 2 raised to power 5 minus 3 x raised to power 3 plus 5 combination 4 2 raised to power 5 minus 4 and x raised to power 4 plus 5 combination 5 times 2 raised to power 5 minus 5 x raised to power 5. Now, looking at this, comparing this with our a plus b raised to power n. Our n is 5, our a is 2, and our b is x. Now, let's simplify this. We know that our 5 combination 0 is 1. And then we have 2 raised to power 5. And then x raised to power 0 is 1. Plus, we know that our 5 combination 1 is 5. So, 2 raised to power 5 minus 1, 4. X. Plus, our 5 combination 2 is 10. 2 raised to power 5 minus 2, we have 2 raised to power 3. X raised to power 2. Plus 5 combination 3, again is 10. 2 raised to power 5 minus 3, 2, x raised to power 3. 5 combination 4 is 5. 2 raised to power 1, x raised to power 4. Plus 5 combination 5 is 1. Times 2 raised to power 0, 5 minus 5, and x raised to power 5. So, simplifying all of this, we have 2 raised to power 5 is 32. 32 times 1 times 1, we have 32 here. Plus 2 raised to the power 4 is 16. 16 plus times 5 is 80. 80 times x, we have 80x. Plus 2 raised to the power 3 is 8. 8 times 10, and we have 80x squared. Plus 2 raised to the power of 2 is 4 times 10. We have 40x cubed. Plus 2 times 5, 10 raised to the power x. 10x raised to the power 4. Plus 2 raised to the power 0 is 1 times 1 times this. And we have x raised to the power 5. So that's that. So you see how this has saved us the work of doing this. X 2 plus 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 x. Those are taking us a long time, but we're able to do, using binomial theorem, we're able to do all of this in 1, 2, 3 steps. Now let's move on to the next example. Number 2, we're given x minus 1 over x raised to the power 3. So 3 combination 0. Our a in this case is x, so we have x raised to the power 3 minus 0. And our b here is minus 1 over x. Minus 1 over x is power 0. Plus 3 combination 1. Our x, then 3 minus 1. Minus 1 over x raised to power 1. Plus 3 combination 2. Our x, 3 minus 2 times minus 1 over x is power 2. And finally, 3 combination 3. Here we have x raised to power 3 minus 3 and minus 1 over x raised to power 3. Now we've already established that 3 combination 0 is 1. Then 3 minus 0 is 3, so we have x cubed. This raised power 0 is 1. Plus 3 combination 1 is 3. 3 minus 1, we have x squared. And then we have minus 1 over x. This is raised power 1. Plus 3 combination 2 is 3. X raised to power 1. That's 3 minus 2. And then minus 1 over x all squared is equal to 1 over x squared. Plus 3 combination 3 is 1. Then 3 minus 3 is 0, so we have x raised to power 0. And minus 1 over 3 raised to power 3 is equal to minus 1 over x cubed. So simplifying this, we have x cubed 3 times x squared times minus 1 over x. This will cancel to give us minus 3x. Move on to the next one. 3 times x times x, we cancel this. So we have plus 3 over x. The next one, our x raised to power 0 is 1. So 1 times 1 times minus 1 over 3. So we have minus 1 over x cubed. Sorry, I meant to say times minus 1 over x cubed. So this is our final answer. So we're able to do this in just 1, 2, 3 steps without having to do this times itself and itself again. Now let's go to the final example. We're given 1 plus x all raised to power n. So in this case, we are not given any specific value for n, but we use our formula anyways to expand this. So n, c, r is 0. So we have, in this case, a is 1. So we have 1 raised to power n minus r, n minus 0. And then our b is x. So we have x raised to power 0 plus n combination 1 and 1 raised to power n minus 1 x raised to power 1 plus n combination 2 1 n minus 2 x raised to power 2 plus n combination 3 1 raised to power n minus 3 x raised to power 3. And this goes on and on and on until we'll get to n combination n 1 raised to power n minus n and x raised to power n. So we don't know what our n value is, but it continues until we get to n, until r gets to n. So let's simplify this. N combination 0 is 1. Anything 1 raised to the power of anything is 1. X raised to the power 0 is 1. So n combination 1 is n. 1 raised to the power of anything is 1. Then we have x plus n combination 2. Now, this is where we go back to some of the things we talked about in briefly touching the operations of combination. We showed that n combination 2 is equal to, let's just briefly work that out here. N combination 2 is equal to n factorial over n minus 2 factorial times 2 factorial, which is equal to n times minus 1 times n minus 2 factorial over n minus 2 factorial times 2 factorial. So this equals to this. So n combination 2 is equal to n minus 1 over 2 factorial. So our n combination 2 will be equal to n minus 1 over 2 factorial times anything raised to power 1 raised to power anything is 1, and then x squared. So as we keep moving, where we have n combination 3, what we are going to have in place of n combination 3 is n minus 1 times n minus 2 over 3 factorial. And anything raised to power 1 is 1. Then x cubed. So it goes on and on and on until we get to n combination 1 with n combination n. N combination n is equal to 1. 1 raised to power n minus n, which is still 1. And then n raised to power x raised to power n. So this gives us 1 plus n times 1 times x is nx plus n times n minus 1 over 2 factorial times x squared plus n times n minus 1 times n minus 2 over 3 factorial times x cubed. So it goes on and on and on until finally we get to 1 times x raised to power n. So that's our answer on that. The next example, we are asked to find the term and coefficient of x cubed in the expansion of 2x plus 3 over x raised to the power of 7. Now what this question is asking is to find the position. That's what they mean by saying find the term. But find the position and then the coefficient of x cubed. In essence, what they're trying to tell us, in the expansion of this binomial, there is a term with the variable x cubed. So we are going to find, what we are asked to do is to find the position of that term and also find the coefficient of that term. Now let's get into it. The general term for the expansion of 2x plus 3 over x raised to the power 0 is equal to, using the general term formula, is equal to 7 combination r. At this point, we don't know what our r is. It's our r. From knowing our r, that we will know the position of the term. Remember, the position is equal to r plus 1. R, in this case, our a is 2x raised to the power of 7 minus r. That is n minus r. And then in this case, our b is 3 over x raised to the power of r. So we'll simplify the general term, which is, we want to simplify this with the aim of separating the constants from the variable x. So let's do that. 7cr 2x power 7 minus r times 3 over x raised to power r. This becomes 7cr. In opening this bracket, we have 2 raised to power 7 minus r and x raised to power 7 minus r. Then also 3 raised to power r over x raised to power r. So what we do now is we kind of collect like terms and separate the variables from the constants. So that is, since all of this is multiplication, we have 7 combination r, 2 raised to power 7 minus r, and then we have x raised to power 7 minus r. We'll also bring out our 3 raised to power r since it's a constant. And then we are left with over x raised to power r. Now remember from our laws of indices that in dividing two indices, what we do is that we subtract the power. So this is also equal to 7 combination r, 2 raised to power 7 minus r, 3 raised to power r is equal to x. Since the bases are the same, we have 7 minus r minus r. So by the time you open that bracket, you have 7 combination r, 2 raised to power 7 minus r, 3 raised to power r, and then 7 minus r will give us x raised to power 7 minus 2r. Now, remember we are asked to find the term and the coefficient of x cubed. So it's safe to say, let's assume the coefficient of x cubed to be a. So we can say a times x cubed is equal to 7 combination r, 2 raised to power 7 minus r, 3 raised to power r over 7 raised to power 7, x raised to power 7 minus 2r. So in this case, r, a being the constant, is equal to 7 combination r, 7 minus 2 raised to power 7 minus r, 3 raised to power r, and then x cubed is equal to 2x raised to power 7 minus 2r. Now, since the bases are the same, this is the formula for our coefficients. We'll come back to this. Since the bases are the same, we can cancel out x and bring down 3 is equal to 7 minus 2 per r. We use this to solve for r. You cross your minus 2 out to this other side, and you have 2r is equals to 7 cross 3 minus 3. So your 2r is equal to 4, and your r is equal to 4 divided by 2, which is equal to 2. So our r is equal to 2. This now tells us that the term is r plus 1, which is equal to 2 plus 1. So the term we are looking for is the third term. Now that we found the term, now let's solve for the coefficient of x cubed. Remember, I've already established we let our a be equal to 7cr. We already established that the coefficient of x cubed is a, we assumed. So in this case, now we know what our r is. So substituting our r into this, we have 7 combination 2 raised to power 7 minus 2, 3 raised to power 2. So we have 7 combination 2 times 2 raised to power 7 minus 2 is 5. So we have 7 minus 2 is 5. So we have 2 raised to power 5. And then we have 3 squared. So this becomes 7 combination 2 is 7 factorial over 7 minus 2 factorial times 2 factorial times 2 raised to power 5 is 32. 3 raised to power 2 is 9. This is equal to 7 factorial over 5 factorial times 2 factorial times 32 times 9. So 7 factorial, 7 times 6 times 5 factorial over 5 factorial times 2 times 1. 5 here, we cancel 5 here. All of this is times 32 times 9. 2 here, we cancel 6. We'll divide 6 to give us 3. So what we are left with is 7 times 3. So we have 21 times 32 times 9. By the time you multiply this, you have 6048. So the coefficient of x cubed is equal to 6048. Here are some exercises for you to practice with. If you found this video helpful, please kindly like and share it with your friends and colleagues. And if you have any questions or run into any difficulty with the exercises or explanations, please drop a comment below. I'll be more than glad to respond. Thank you.